Good afternoon. Here is the lesson on static electricity and magnetism. It is lesson 4A, which is static electricity, page 12 in your Cornell notes, and number 4B, magnetism, page 14 in your Cornell notes. You should have received both of these sheets in class. Static electricity. You walk across the rug, reach for the doorknob, and zap, you get a shock. Or you come inside from the cold, pull off your hat, and boing! What's going on here? And why is it more of a problem in the winter? To understand static electricity, we have to learn a little bit about the nature of matter. Or in other words, what is all this stuff around us made of? First, we're going to watch a static electricity brain pop clip.
Ow, why'd you do that? Oh, thanks, I guess. Dear Tim and Moby, why do I sometimes get zapped when I touch a doorknob? From Sarah. That's an example of static electricity. Electricity is when electrons, the negatively charged particles in an atom, move from one place to another. In current electricity, the kind we use for power, there's a steady flow of electrons along a circuit. In static electricity, like lightning and those pesky doorknob shocks, there's usually a single sudden transfer of electrons from one place to another. In order for that transfer to happen, you have to have a buildup of electrons on a surface. Hey, what are you doing? Right now, Moby's building up an electric charge. The rubbing makes the balloon pick up electrons from my hair, giving it a negative charge. Because my hair loses those negatively charged electrons, it gets a positive charge. And the negatively charged balloon attracts the positively charged hairs on my head. Because opposites attract, right? I think it looked better before. Anyway, all the matter in the universe is made up of atoms. And every atom contains a certain number of protons, neutrons, and electrons. Protons have a positive charge, and electrons have a negative charge. Neutrons don't have any charge at all. So, when an atom contains the same number of protons and electrons, it has no overall charge, and it's considered neutral. Protons and neutrons are stuck in the nucleus of the atom. But electrons orbit the nucleus, kind of like the moon orbits the Earth. And electrons like to move around. In fact, if you rub two non-conductive materials against one another, those electrons can jump from one material to the other. What are non-conductive materials? Well, conductors are materials that electrons flow through easily. Metals are good conductors. Non-conductive materials, or insulators, don't allow electrons to flow through them. They include things like cloth, rubber, and plastic. Some insulators like to give up electrons, and some of them like to collect electrons. Most carpets are made of nylon and wool. Those substances tend to give away their electrons, leaving them positively charged. Your shoes, on the other hand, have rubber soles, and rubber is a material that naturally collects electrons. Remember how the rubber balloon pulled electrons away from my hair? Well, your rubber soles can pull electrons away from the carpet. All you have to do is walk across it, and the electrons will be pulled out of the carpet and onto the soles of your shoes. A force called adhesion is responsible for the transfer of electrons. You can build up a bigger electric charge by rubbing your feet against the floor. The more you do it, the more electrons your shoes will collect. Anyway, those electrons that your shoes pull away from the carpet stay stuck to the surface of your body. And if you touch a conductor, like a metal doorknob, the electrons will flow out from your body and into that conductor. And they'll do it really, really fast. The shock you feel when you touch a doorknob is millions of electrons flowing between you and the knob in like a split second. That's a lot of energy to transfer in a really short time, which is why shocks can be painful. So, if your home has carpeting, be careful when you're wearing shoes indoors. Right, Moby? Moby? least no one can see my hair now.
Okay, so since you've seen that brain pop, now we can take some notes. First off, let me grab the highlighter. Everything is made of atoms. This is right on your note sheet. So in the blank, you are going to fill in atoms. Everything is made of atoms. Secondly, atoms are made of protons, which are positive. They have a positive charge. Neutrons, which are neutral. They have a neutral charge, so they're not positive or negative, and we represent that with a 0. And electrons, which have a negative charge. And that's the little minus sign there. Underneath that, you have the drawing of an atom. So right here, I would like you to draw in that space in your notes where it says draw an atom. You're going to draw in 2 circles with the positives in them. That stands for 2 protons. You're going to draw in 2 empty circles. Those stand for the neutral neutrons. And thirdly, on the outer ring around what's called the nucleus in the middle here, where the protons and neutrons live, is this is where the electrons actually spin, and the electrons are negative, and they actually orbit the nucleus. Next to where you draw that, you need to write in that electrons can be ripped away from the atom, and that protons and electrons are generally balanced, making an electrically neutral material in general. So if you notice here, there are 2 protons and 2 electrons. So 2 positives and 2 negatives equals 0. So if you have +2 and a -2, it's a 0. So this atom right here would be a neutral atom. Static electricity happens when you don't have a neutral atom anymore. It's when you have a buildup of charge, a difference in charge between atoms. Moving on. This is also a diagram on your sheet. It's the next one down. And this didn't show up as well on my screen as it is on your paper. However, underneath positive charge, you'll notice that there are more positives than negatives. So more protons than electrons, which means it's unbalanced. This means that electrons were removed from the atom, which left more protons, which meant that it's a positive charge. And so I want you to write this in. So what's in blue here you need to write in. The next one over is a neutral charge. There's no charge because it's neutral. The electrons equals the protons. In the third one, there are more electrons than protons because this material managed to acquire or get more electrons. So electrons were added, which made it negative. Now, there are some other terms underneath here. An insulator is when electrons aren't moved easily through a particular material. An example of an insulator might be plastic or glass, cloth, or dry air. Again, electrons do not move easily through these things. Another word on your sheet is a conductor. Now, these materials do move electrons easily through them. An example of that might be metals. Those are good conductors, electron conductors. Okay. Next up. So how do we move charges anyway? How do we move electrons from one object to the other? I'm going to show you a short video clip here, and what it demonstrates is when one material is rubbed against another one. And up here, tells you what I want you to write down in that space. So you rub materials together, electrons are transferred, they're moved from one object to the other. So again, you need to write this down right here, where it says, how do we move charges? This is the answer. And now I'm going to play this video clip.
This is an example of how static electricity works. Rubbing a glass rod with a silk cloth causes the rod to acquire a positive charge. When this rod is touched to aluminum foil spheres, the rod shares some of its positive charge with the spheres. The rod and spheres then repel each other, as do the two spheres if they are brought together. Rubbing a plastic rod with a wool cloth causes the rod to acquire a negative charge. When this rod is touched to aluminum foil spheres, the rod shares some of its negative charge with the spheres. The rod and spheres then repel each other, as do the two spheres when brought together. When a positive sphere is brought near a negative sphere, the two will attract each other.
Great. Moving on. At the bottom of your page, you see a section that says opposites attract. And what I need you to write in, or draw in rather, is this right here. Opposites attract. And you see one yellow rectangle being drawn to another one, and the opposite charges are actually attracting to each other. So you have a positive charge and a negative charge, and they're drawn toward each other. Underneath that, I want you to draw in the opposite, which is like charges repel. And I want you to draw this in. So if you have a material that has, or two materials that both have negative charges on them, they're going to repel from each other or push away from one another. Also, if you have two materials that have positive charges on them, they're also going to repel or move away from each other. Finally, I have a short Bill Nye clip.
Now suppose we want to make a big static electrical charge. Well, we could use something like this. This is called a Van de Graaff generator. It's named after Robert Van de Graaff. So here's what happens. Electrical charges are deposited on this rubber belt. The rubber belt turns and redeposits the electrical charges up here on this metal ball. Now, since this next part of the demonstration rocks, I'm going to put on my rocker wig of science. Yeah. Start the rubber belt turning. Electrical charges are being deposited on the metal ball. They're running through my arm and being deposited in me. And look, it's building up in my rocker wig of science. See, since these charges are all the same, they're not attracting. They're repelling. They're pushing apart. So they're pushing the hairs of my rocker wig apart. Now, if I could find a way to get these electrical charges off of me back into some other parts of the room, the hairs wouldn't repel each other. There wouldn't be a static electrical charge. No, the charge would jump. Let's try it. Watch what happens when I bring this ball near this ball. See the spark? The charges jumped. The static electrical charges aren't static. No, they jumped. Static electricity. It rocks. See that? It sparked.
Next up, we have magnets. So turn to page 2 of your notes. Actually, it would be page 14, and it would be lesson 4B, magnetism. The two questions we're looking at are, what are the properties of magnets, and how do magnets attract and repel? First off, we are going to watch another brain pop.
Call robot repair shop, Ray Magnets. Dear Tim and Moby, why do magnets stick to things? From Jen. A magnet is any material that produces a magnetic field. Yeah, a magnetic field is basically a force field. It's an invisible area of force that extends all around a magnet. That force attracts metals like iron, nickel, and cobalt. When those metals fall inside a strong enough magnetic field, they become temporarily magnetic. Well, all metals have arrangements of atoms inside them called magnetic domains. Usually, the poles of these domains are jumbled up, so they pretty much cancel each other out. But the domains inside of a magnet are a different story. In a magnet, all of the domains are lined up so that they face in the same direction. That creates a magnetic field. The magnetic field temporarily lines up the magnetic domains in the paperclip, so it becomes a magnet too. Magnetic fields get weaker the further away from the magnet you go. So if the paperclip is too far away, the magnet can't pull it in. Right, every magnet has a north and south pole. In fact, if you cut a magnet in half, the two magnets you're left with both have north and south poles. It's true that opposites attract. A north pole will attract a south pole. But try to get one north pole together with another north pole, and they're just not interested. You can force them together, but they repel each other. Any magnetic metal has north and south poles too, and weak magnetic fields surrounding them. Oh, magnets get their name from a type of iron ore called magnetite. Thousands of years ago, people in ancient Greece and China noticed magnetite's strange properties. When small pieces of iron were rubbed against it, those pieces would start to act, well, kind of funny. When the pieces were free to turn, one end always pointed north. Yep, those pieces of iron were the first compasses. Compasses work because the Earth has its own magnetic field, with magnetic north and south poles, slightly offset from the geographic poles. It pulls at lightly balanced pieces of metal, like a compass needle. That's why a compass needle always points north. Magnets have tons more uses besides compasses, though. Electromagnets are everywhere, in electric motors, circuit breakers, doorbells, you name it. Oh, when you run an electric current through a piece of wire, it creates a magnetic field around the wire. That's an electromagnet. You can control the strength of the magnetic field by changing the amount of electric current you run through the wire. Oh, sure, robots are built with electromagnets too. Hey, what do you think would happen if you turned up your current? You okay there, buddy?
And now we're back to the notes. First, on your note sheet, you have what are the properties of magnets. So write this down. Wherever I put a star, we have magnets have a north and a south pole. Magnets have magnetic fields. And the invisible force field around a magnet that attracts iron, nickel, and cobalt, well, that is a magnetic field. Sorry if I said that strange. So a magnetic field is the invisible force field around a magnet that attracts iron, nickel, and cobalt. And what parts of the magnet have the strongest magnetic field? That is the poles. Okay. I also need you to draw in this diagram here. That is very important. So draw in the bar magnet with the north and the south pole. And then you have to have at least two of the lines coming from the north pole going into the south pole on each side. Notice the direction of the arrows. That it does come out of the north and go into the south pole. That is the direction of the magnetic field lines. What is magnetism? So what is a refrigerator door closed? Most refrigerator doors are kept closed by magnetism. Magnetism is a pulling force that certain metals have. So everything highlighted in yellow is what you need to write down. These metals, called magnets, attract and repel other pieces of metal. Attract means that two objects pull toward each other. Repel means that two objects push away from each other. All magnets have two ends called poles. Each magnet has a north pole and a south pole. The north pole of one magnet attracts the south pole of another magnet. Both the north pole of one magnet repels the north pole of another magnet. Two south poles also repel each other. In some ways, Earth acts like a magnet with two poles. You can tell by using a magnetic compass. A magnetic compass is an instrument with a magnetized needle. One end of the needle always points to the magnetic north pole of the Earth. Sailors use compasses to tell what direction they are going. Magnets do not have to touch a piece of metal to attract it. There is an attracting area around every magnet called the magnetic field. When a piece of metal comes near a magnet, it is attracted by the magnetic field. The attraction gets stronger as the metal gets closer to the magnet. And finally, for B, which is how do magnets attract and repel, at the bottom of your notes, we have this. We have the Earth has, every magnet has two ends that behave differently. One end is called the North Pole and the other end is the South Pole. The Earth has two poles very much like a magnet's poles, a north and a south pole, so we had said this. Two north poles always repel each other. Two south poles also repel each other, but north and south poles attract each other. So here you see two north poles repelling. Here you see a north and a south attracting. These are the notes you need to write down though. So how do magnets attract and repel? So I want you to draw this bar magnet here and draw the field lines coming out from the north going into the south pole. And I want you to write this here. Field lines move from north to south. Then I want you to draw these two bar magnets right here. So the north poles are facing each other. Notice that the field lines are coming out of the north going into the south on both the magnets. All right, and then write this over here. We have these repel. The north and north field lines bump into each other. So this is the space where the magnets are repelling because the field lines are bumping into each other. Here we have a north and south end close to each other, and the north and south field lines attract. So I want you to copy that down as well. Make sure that you put the north and south poles in the same positions on here. And that is it for your notes.